Okay, so this is for chapter 13. Okay, the first question is which of the following substance is the most soluble in benzene and non-polar solvent? So depending on the molecular structure, and we will see how much non-polar parts in the molecular and how much polar parts. So for these four given programs, they all have the same number of carbon atoms, 1, 2, 3, 4, 5 carbon. Um, so those parts have a carbon bonded to H are nonpolar, whereas the carbon bonding to carbon or H bonded to O, or carbon or H bonding to halogens are polar. Why? Because we learn in chapter in Chem 113, so the bond polarities depend on the electronegativity difference. So we talk about those bonds between carbon or H2O or carbon to H. So those chemical bonds have those polarities. So these polarities depends on the delta En. So delta En standing for the difference in electronegativity. Difference in electronegativity. All right, so you can see there's a table for the electronegativity of those common elements. And for example, for H, you have 2.1. For carbon, you have 2.5. So therefore, the chemical bond between C and H, you think about this chemical bond is polar, non-polar, you will use the electronegativity difference. So let me just stop the video. I think the bandwidth will be better. So the CH bond, and if you think about the CH bond, this two atom carbon and H, if you calculate what is the delta En, and that will equals, let's say you will take the larger number, 2.5 for carbon, and minus 2.1 for hydrogen, so you get 0.4. So there is approximately guiding line for the polarity of the chemical bond, which means depend on the difference of the electronegativity. So if the delta En is less than 0.4 or less equal to 0.4, so those kind of bond we say nonpolar. Otherwise, if it larger or equals than 0.5 and smaller than 1.9, so those are polar. If they are larger than 1.9, larger or equals 1.9, then we consider them as ionic. But those guiding line is approximate. Larger equals 1.9. So usually those approximate guiding line is good enough to solving most of the problem. For example, for our problem, we can see the delta En between carbon and H is 0.4. So according to this, which means the bond between carbon and H are nonpolar. That's the reason we see for those molecules, we have the non-polar part and the polar part. So this full molecular, there's no polar part at all. So definitely that one is non-polar. For this one, if I circle those C and H, so they are non-polar. And then we have a small part which is polar. And this one have two of those small parts are polar and polar. And here there's one small part between carbon and a halogen, which is chlorine, so that's also polar. All right. So you might argue, let's say, if you have two of those polar, will they cancel out? But the answer is no, because those bonds are freely rotate. So even though in this structure, it looks like O and H on this side, O and H on the right side, they kind of cancel out. But this is just not a reality. So in reality, those chemical bonds they are not really on one line, or the probability or the chance for these two bonds on one line is very, very small. Therefore, they do not cancel out. So as a result, this is most polar, this is second most polar, this third most polar, then that's just non-polar. So the rule of thumb is like dissolve like. Like dissolve like. What I mean by like? Like means polar dissolve in polar, non-polar dissolve in non-polar. So if I give you a solvent like benzene, and you want to choose the most soluble one in benzene because benzene is non-polar, so therefore the answer is A. That's our answer. All right, second question is using Henry's law, calculate the solubility of a gas in the in the solvent, like in water. So you just use Henry's law. So Henry's law written as S gas equals K gas times partial pressure of a gas. So then depending on the problem, the gas may be oxygen, maybe nitrogen, maybe carbon dioxide. So in this example, our gas, the carbon dioxide. So therefore we write SCO2 equals KCO2 times the partial pressure of CO2. So then just identify, do we have the number for KCO2? Do we have the number for PCO2? Yes, we do. So we have KCO2, the Henry's law constant is KCO2. So therefore, we have 3.4 times 10 to the negative 2. The unit is more on the top. And then we have L, then that means subtracting, that means they all together at the denominator. So then you just multiply by the given partial pressure, 3.5 ATM. And then you can see this ATM cancel out. So you take those number multiply. The only unit left over is mole over liter. And then the number is 0.119. So mole over liter. Then you check the sig figs. This only have 3.4 only have 2 sig figs. 2 sig fig. So therefore, our final answer running to 0.12, and we can call that a capital M. So this number, this 0 does not count as a significant. So 1, 2 counting as 2 significant digits. So therefore, our answer is this, which matching the answer C. Okay, so question 3 is very similar as what we just did for this question 2. You can just write up the Henry's law equation. So you write in general, you call that solubility of a gas, so S gas equals, depending on the gas, we have different K, so therefore we write K gas then times the partial pressure of the gas. Okay, so when temperature is constant, when temperature is kept constant, then the key gas is constant. And obviously, the constant key gas depends on the gas, right? So now for a given gas, the question is if you triple the P gas, and this equation tells us so K is a positive number, so therefore it's linearly directly proportional. So if you triple the P gas, then your S gas triple. Well, what is S gas? S gas is written as molar solubility, which means moles over liters. So your volume did not triple, just triple the moles. If you triple the moles, that means at triple times as many gas molecules in the liquid. So therefore, the answer is D. Okay, so question number 4 is a solution is made by dissolving 23 gram of glucose in 0.100 kilogram water. What is the mass percent of the solution? What's the mass percent of the solute in this solution? Okay, so our solute is the glucose. So that equals 23.5 grams. And then by definition, so mass percent equals mass of a component. Your component can be one of the solute or the solvent. Then more mass of a solution. All right. So just know mass of a solution equals everything together. So mass of a solution equals mass of a solute plus mass of solvent. For this question is simple. We only have one solute and one solvent, always one solvent. So therefore we have 23.5 gram plus that guy you have to convert because this is a kilogram. Then we know 1 kilogram is 1,000 grams. So therefore we get 123.5 grams. Okay, then what you do, you just go by the formula. So let's use abbreviation percent mass of glucose for equals mass of glucose, which is 23.5 gram divided by the total mass of the solution, which is 123.5 gram, then times 100. Okay, so what you get is 19.0%. So the answer is B. Okay, so next question, very similar. You want to calculate. So you want to calculate the parts per million. So we'll write the definition. So parts per million equals whatever you want to calculate the parts per million for what. We'll call the components. So for this example, your component is zinc. So therefore, we'll say mass of zinc zinc 2 plus ion divided by mass of solution. Then times 10 to the positive 6. All right. So then you just do some conversions. Let's say I will do the conversion in the formula. So I have a 7.4 microgram. And then we know for every 1 microgram, the 10 to the negative 6 gram. So this comes out. And then in the denominator, you will take the mass of the water, then plus the mass of the zinc. So you do the same conversion here, then times 10 to the 6. Okay, so it's a cancellation here. So in reality, you can see these two numbers compare 2.5 with 7.4 times 10 to the negative 6. So this number is really, really negligible. But with the modern calculator, you can just add in and then divide into the top. Okay, so therefore, what you get is 3.0 parts per million. And this will matching the answer D. Okay, so next question is very interesting, maybe a little difficult. And you have a commercial bleach solution contain 5.62% by mass of NaOCl in water. So you have two parts of the question. First, you calculate the mole fraction, then you want to calculate the molality of NaOCl in the solution. Okay, so part A. And how do you calculate mole fractions? Calculate mole fractions, you have to know the mole of all the components. So to get moles, you have to know the mass and molar mass. So therefore, we starting by assuming we have 100 grams of the sample. So if you assume you have 100 grams of sample, you have this mass percent. Okay. So what is mass percent standing for? You can write as 5.62 gram NaOCl over 100 gram of the sample. Now, because we are assuming we have 100 gram samples, therefore we will take 100 gram sample, multiply onto our mass percent, and we get 5.62 gram NaOCl. Okay, so that means in every 100 gram of sample, so we have 5.62 gram of NaOCl. Well, altogether you have 100 grams. So you have 5.62 gram of this NaOCl. So then how much the other one? The other one is water. So we'll take 100 gram of the sample minus 5.62 gram of NaOCl to get the gram of water. So you simply do a subtraction, get 94.38 gram of H2O. So now you have two components, and now you know both of their mass, and you want to find a mole fraction, you have to know both of their moles. So therefore, you need the molar mass. So molar mass of NaOCl will equals 1 times the mass of Na. You do to the periodic table, you see that's rounding to 22.99. Then plus 1 times oxygen, so rounding oxygen to 16.00. Then plus 1 times for the chlorine, 35.45. Okay, multiply and add, so we get a molar mass for NaOCl, 34.44 gram per mole. Similarly for water, so we see what is molar mass of H2O, And we can see we have 2H and 1H is 1.01. Then we have one oxygen, so 1 times 16.00, so get 18.02 gram per mole. All right, so once we have the mass and the molar mass, now let's do the calculation for the moles. We started that in Chem 113, so we start with one example for one in NaOCl. We have 562 grams of NaOCl. We usually use the pico-Farads way, so that means system over one. One have no unit, and then we have 1 mole over 74.44 gram. So gram cancel out, we get how many moles of NaOCl? 0.0755 mole of NaOCl. Similarly, do the calculation for the mole of water. We start with 94.38 gram of H2O, and we say this just over 1. The molar mass of water is 18.02 gram for 1 mole. And we have 5.24 moles of H2O. So once we have that, and we can see the mole fraction of NaOCl will equals mole of NaOCl divided by mole NaOCl plus more H2O. All right. So therefore, we can see and get some more space. Okay, so now we will continue to write the mole fraction, and we know the mole of NaOCl, so that will be 0.0755 divided by 0.0755 plus 5.24, and then we get 0.0142. So this is one part of the answer for part A. Okay, so for part B, we want to find molality. So that's usually called the little m. So little m will equals moles. If you want to find the molality of NaOCl, will be mole of NaOCl divided by kg of solvent. And in this case, our solvent is water. So we need a kilogram of water. You can do a conversion in the calculation, but I probably will do the conversion here because we know we have 94.38 grams of H2O. So H2O is our solvent. And then you know how to convert from gram to kilogram. So we have 1,000 gram in 1 kilogram cancel out. We have 0.09438 kg. All right, so then you just do the dividing now. So we just, from part A, we know the moles of NaOCl is 0.0755 mole of NaOCl, well divided by the kilogram of our solvent, which is water, so 9438 kg solvent, and we get, so depending on how we rounding, so this time I get 0.7999 something, so I round into 0.800, in the answers, you probably will see 0.801, so doesn't matter. So you can see this will be measured answer E. So leave off then the given question. So given answer given question 0.801. Probably I did not running in the calculation when I post the questions. So now I running them all to those 0.755 and so on. So therefore I get the different answers. All right. So now question number 7 is give you the density and then give you 100 gram of the sample contain 87 milligram of calcium. Then you want to calculate the molarity of the calcium in this maple syrup. So we know by definition molarity equals mole over liter of the solutions. And so you can think about the definition, and then let's see, the definition is the molarity. Okay, so molarity equals mole. You want to find molarity of calcium, so that means mole of calcium ion divided by liter of solution. Liter of solution. So you're going to find out more of calcium ion. You also need to find out the liter of solution. Those information do not give you directly. So first, let's find out more of calcium ion. Well, depend on how much sample we have. So again, we'll begin to assuming 100 gram of sample. Okay. So you can see there's tell you 100 grams of sample, you have that much. So therefore, we have 87 milligram of calcium. So now you do a conversion, right? So you know like 1 gram is 1,000 milligrams. Milligram comes out. That means we have 0.087 gram of calcium 2 plus. Now you want to use molar mass. So we'll see molar mass of calcium 2 plus ion. That's simple, just 1 calcium. You go to the periodic table, you find that is 40.08 gram per mole. So therefore 0.087 gram calcium and divided by 40.08 gram and get how much moles. So we get 0.00217 mole of Ca2 plus. Okay, so this is what you want to find out, molarity. You need mole for calcium, you need liter of solution. So we find out mole for calcium. Next, let's find out the liter of solution. So to do that, we need to use this density, and we need to use this assumption. We assume we have 100 grams. So in 100 grams, we have this much more of calcium. Then this 100 gram of solution has how much volume? So what you do, you will use density, because density is about the solution. Okay, so you can see if you write 100 gram of our solution, and then the given density is 1.325 gram per ml. So you first 1.325 gram solution for 1 ml. So the gram solution comes out. You get how much ml, and obviously you want to get L. You have to divide the number by 1,000. And you get 0.0755 liter of solution. Okay, now you know both numbers in this definition of molarity. So therefore, we are ready to put the mole and the liter of solution in the formula and do the calculation. So we will use 0.00217 moles over 0.0755 liters, and you get 0.029. I run into the number of sig figs, 2 sig figs, because 87 has 0.087 only have 2 sig figs. So this answer is A. Okay, so question number 8 is about freezing point depression. You want to calculate the freezing point of a solution containing 0.600 kilogram of CHCl3 and 52.0 gram of this compound. And so this compound is an organic compound. We can think this compound is non-electrolyte. So you will see those information in the formulas. You want to calculate the freezing point of solution. So one formula was written as this way. So we call the TF is the freezing point. Freezing point for what? We use parentheses of freezing point temperature of a solution. I use solution minus TF, which means freezing point of solvent. I just write solvent equals negative IKF and little m. So those you saw them before. So I is the 1.5 factor. KF, see here the given KF. KF is given for the solvent. Little m the molality. So for this given problem, did not tell you directly who is solvent, who is solute, but from the information you can find out the solvent is CHCl3. The solvent is CHCl3. Okay. And it has the freezing point TF equals negative 63.5 degrees Celsius. Okay. And then let's see, so therefore we have this information. We need to find out this. So this TF solution is the question mark. So this is the question mark. All right. So we know this number now, and we have to know the rest. So what is I for a non-electrolyte? We can see because our solute has a formula C10H18O is a non-electrolyte, which means when you put this C10H18O in the solvent, it keeps intact, does not separate. We also assume it will not coagulate, does not come together. Therefore, we will say this I equals 1. For the given problem, we find out the KF. So KF is given 4.68 degrees Celsius over little m. Okay, so this is what we find out. You know that you need to know this. You need to know I. You need to know KF. So those are checked. So the next question is you want to find out the little m. So we know how to calculate the little m from the previous questions. Okay. Okay, so little m or equals more of C10H18O divided by kg of CH3Cl, or the opposite. CHCl3. All right. So therefore, we need to calculate what is the mole of C10 H18O and what is the kilogram of CHCl3. Well, so kilogram that is given, so we can just list up here. So kg of CHCl3 is given 0.600 kg. So that's ready to put into this formula. So next, we want to find out more of this. So what is given about this C10H18O? Well, it's given grams. Then you know if you want to find out more from gram, what do you need? You need molar mass, right? So molar mass of C10H18O equals, we have 10 carbon, so 10 times 12.01 from the periodic table. We have 18H, and then we have 1.01 from the periodic table. Then we have 16.00, only one 16.00 for 10. So we get 154.28 gram per mole. Right, now next, we will take the given gram, right? If I go back to the question, so the gram of this C10H18O is 52.0 grams. So we write 52.0 gram C10H18O over 1, it means nothing, no unit. And then we have 154.28 gram for 1 mole, and we get 0.337 moles. So now we are ready to get little m. So therefore, little m will equals 0.337 divided by 0.600. So that's mole, and this is kg solvent. kg solvent, and we get 0.562 little m. Right. So now we have everything in this equation except that one. Right. So we have Tf for solvent negative 63.5 degrees Celsius. Our I is 1. Our Kf is 4.68. Our little m we just find out is 0.562. Now let's plug all those into the equation and solving for our unknown. We write Tf solution minus, initially in the formula is Tf solvent, and that becomes negative 63.5 degrees Celsius equals negative I, so I is 1. Kf is 4.68 degrees Celsius over little m. Then we have this much little m. So little m comes out, this is 6. And we have a degree Celsius, okay? So therefore, if you can see the, get some more space here. Okay, so let's write up what we have so far. So we'll write Tf solution, which is what you want to find out. And now minus and minus become plus, therefore plus 63.5 degrees Celsius. Then here on this side, if you take negative 1 times 4.68 times 0.562, you get, still have the negative sign here, the negative 2.63 Celsius. So obviously you can solve this equation. So Tf will equals negative 2.63 Celsius minus 63.5 Celsius. So get negative 66.13 Celsius. And this will be our answer B. Yeah, negative 63.13, probably we'll just use negative 66.1. All right, so the next question is, you have given a few solutions, and you want to find out the lowest freezing point, okay? So what you do, you can say those are aqueous solutions, means water is the solvent. So then we know TF of solvent or TF of water is 0 degrees Celsius. 0 degrees Celsius. Okay. So therefore, our equation we saw in the last questions, we write TF solution minus TF solvent equals negative IKFM can be simplified into this. So can simplify into TF of our solution, that becomes 0. So that's minus 0 equals, we have some number for KF for water, but this will be just constant. So therefore, let's write like in front. The negative KF first, then times I times little m. Okay, so 0 is 0, so therefore our final formula for the TF of our solution will equals negative KF for water, so everyone will have the same number. So now what make a difference is this I times little m. If we want to find out what is I, we have to see those compounds. So the first compound is CaCl2, which is a strong electrolyte. Why? Because it is ionic and soluble in water. So that's one definition of a strong electrolyte. So if the compound is ionic and soluble in water, then it is a strong electrolyte. What that means? That means if you have a CaCl2 and you dissolve it in water, as it dissolve in H2O, then what happens is you don't have any, ideally, okay? So you don't have any those CaCl2 together anymore. What you get is Cu2 plus ion, then you have 2 Cl1 negative ion. Okay. So therefore, this I will equals 1 plus 2. This is expected or ideally. Okay. So where the 1, where the 2 come from? So if I highlight, and so these 2 come from these 2. Okay. Where's 1? Well, 1 number we did not write. So there's 1 here. Okay. Therefore, this 1 actually come from this one. So that's how we how do we find out the expected. So this is how we find out the expected the 1.5 factor. Okay, so this one here and this one here. So 1 plus 2 is 3. So now you are ready to see the next one. So So the next one is NaCl. So similar reason, what do you think? What kind of compound is NaCl? It's ionic, right? So if it's ionic and is it soluble in water? Yeah, it's good. So we know like NaCl, the type of salt, is soluble in water. So therefore, it is a strong electrolyte. So a strong electrolyte, which means it will dissociate completely in water. And so therefore, we can write up the equation. If we have one NaCl, so NaCl, and let's say dissolve in H2O, it will become Na plus ion, then and Cl one negative ion. So then, what is our expected 1.5 factor? So similar. So you produce one Na, you produce one Cl. So 1 plus 1 equals 2. Okay. So next question is HCl. So HCl is not ionic, but we know it is strong acid. So strong acid is also that is a strong electrolyte. So strong electrolyte. So that's also completely dissociating water. So you can see I draw one headed arrow. That means this reaction is heavily favors the right side. So I equals 1 plus 1, then it's 2. So next one, what you have is CH3COOH, which is the acetic acid. CH3COOH is acetic acid, which is a weak acid. So weak acids do not 100% ionize. So if we write a formula or the equation for the CH3COOH in water, we will usually write two-headed arrow, which means can go forward, can go backward. And sometimes you want to use the lines to representing how it goes. So if I draw the lines going backward, the longer that means the favor the left side. So if you go to the right side, or it will produce H plus, then CH3COO negative. So it's not 100%. So for our I, for less than 1 plus 1, which is 2, or more than just 1, possibly can produce a 2. So that's I for the acetic acid. The last one is our sucrose. We have C12H22O11 is a non-electrolyte. So for non-electrolyte, I just equals 1. Right, so now we have all those I. Now we will combine with our given molarities and make a table. Okay. So let's see our solution here. I'll make a table, and then let's see our I. Then our I times little n. Okay. So our first solution is 0.050 molarity of CaCl2. All right, so this is a CaCl2. Let's see, this is the X expected I. So our expected I will be 1 calcium ion plus 2 chloride ion, which is 3, as we reasoning on this equation before. Okay, and then you will take this 3. So here I times m. So 3 times 0 0.050, 0.150. Next solution is 0.15 liter m NaCl. So what is the expected I for NaCl? Is 2. Okay? Because we can think of for every 1 NaCl, it dissociates into 1 Na and 1 Cl. So 1 Na plus ion, 1 Cl, 1 negative ion, so you have 2 ions, therefore 2. So 2 times 0.15, 0.30. Next is 0.20 liter m HCl. So HCl is a strong acid. It's 100% ionized into, for every 1 HCl, you are 100% ionized into 1 H plus and 1 Cl, 1 negative. Therefore, you have 2 ions again. So 2 ions, that means I is 2. So you take 2 times 0.20, get 0.40. Next question is 0.05050 liter m CH3COOH. Remember, this I is larger than 1, smaller than 2. So in the lecture, I just take the 2 multiplied of that just for simple comparison. But if you take this I more than 1, less than 2, multiply onto 0.050, so this I times m will be more than 0.50, but less than 0.10. Okay, so I take 1 times 0.050, get this number, a lower limit. I take 0.050 times 2, I get the upper limit. And the last solution is the sucrose. So sucrose concentration is 0.20 molarity C12H22O11. And because this is non-electrolyte, so therefore I equals 1. 1 times, so we still get 0.20. Right? So this column will be important for our comparison. So you want to compare this TF of a solution. So if we go back to our beginning of the question, we simplify this into this equation. Okay? So TF equals negative KF times IM. So you can use the number for KF and use those number for IM, multiply, see who has the most negative, or you can simply compare. So all of them, we compare this 5 solutions, this all same for 5 solutions. What means 5 solutions? This is the 5 solutions here. Okay? They are all the same number. So therefore, the larger the IM, the most negative. So the larger the IM, the lower, the more negative the TF solution. Okay, so what do you think? Which one has the largest I times M. The HCl. Okay? So 0.40 is the largest number. If you take 0.040 here, it will give you the most negative. So therefore, the answer is this. So the answer is C. Okay, so last question, question number 7. Now question number 10. So we have a protein, and so protein frequently produce complexes in which 2, 3, or more, or even more individual protein interact specifically with each other with hydrogen bonds or electrostatic interaction. So the entire assembly of protein can act as one unit in solution. And so this assembly is usually called the quaternary structure of the protein. Suppose you discover a new protein whose molar mass is 25,000 grams per mole, and you measure osmotic pressure of your protein, and you suspect maybe it produces a complex. So you measure the osmotic pressure, you get 0.183 atm at 37 degrees Celsius. How much protein you take? You take 7.20 grams of the protein. How much solution you prepare? You prepare the 10.00 milliliter of the aqueous solution. Then you want to calculate how many protein monomer in the quaternary structure of the solution. So we're treating the solution as non-electrolyte. So therefore, we're using our osmotic pressure equation, very similar as ideal gas equation. So we just give that a different name, call it the pressure, not pressure, call it pi equals I times capital M times R times T. So now we know our non-electrolyte. So that's it, because it's non-electrolyte, or use abbreviation, so I equals 1. Okay. So this same as ideal gas equation, very similar as PV equals NRT. So therefore, we know R is a gas law constant, and in this type of calculation, you want to use this number, which has unit atm times L over mole over Kelvin, and the temperature should be in Kelvin, so give you 37 degrees Celsius, you have to convert into Kelvins. So that becomes 310 Kelvins. So then we are given the pressure pi is 0.183 atm. So pretty much we know everything except the capital M. Okay. So capital M is molarity equals mole over liters. We need to find out this capital M. So what do we do now? Just substitute all this information into this osmotic pressure, and we will find out the capital M. So 0.183 atm equals 1 times M. We don't know, we just write as unknown, 0.08206. And then we have the atm times L divided by mole divided by Kelvin. And we have our temperature in Kelvin, 310 Kelvin. Cancel Kelvin out. So next, we just divide these numbers and find out what our capital M. So 0.183 3 ATM divided by 0.08206 ATM times L divided by moles, then here is also 310. So the ATM comes out. So that equals capital M. And so capital M from these few numbers calculation, so we get 0.00719. Right. So what we do next is use the volume and also this find out this capital M to find out how many moles. Okay, so if we write 0.00719, capital M is mole over liters. Okay? So if we know how many total liter, we multiply by the total liter, we will get moles. But before that, you know our 10.0 ml, and you do a conversion. So you see 1,000 ml is 1 L, so 0.01000 L. So now we will take this two number multiply, so the liter cancel out, and you get how many moles. So we will use scientific notation, so we get 7.19 times 10 to the negative 5 moles. So now we know molar mass equals mass in gram divided by moles. So we are given, we say we use 7.20 gram of our protein. Then we know in this 7.20 gram of protein, we have 7.19 times 10 to the negative 5 moles. So therefore we divide, we get 100,139.8 gram per mole. So this obviously is much larger than the 25,000 for one protein. So we'll find out the number of protein as in the complex, in the protein complex, so equals this molar mass divided by the molar mass of one protein, which is 25,000 grams per mole, and we get 4.00556, and we run into 4 because we cannot have like a half protein. Okay, so therefore, we can check that the answer is 4, so it's D. Okay, so that's for chapter 13.